Module 4, Lecture B, Writing and Organizing. By the end of this lecture, you will be able to write computed engineering results to text files with clear labels and units, organize reusable calculation functions in separate Python modules, and create a small repeatable workflow that reads input data, computes results, and writes a report. Writing engineering reports. Writing results. Saving engineering calculations as text files creates simple, shareable reports that remain available after a program ends. These files record important results such as deflection or power values, so others can review, store, email, or include them in design documentation. This supports both traceability and communication in engineering work. Results files should be understandable without returning to the original code. Include enough context to show what each number represents, such as identifying stress versus load or displacement, and separating heating, cooling, and lighting energy demands. Clear labels and descriptions make results easier to interpret later and support better engineering decisions. Writing results to a text file should be part of a repeatable workflow, helping document outcomes and compare scenarios such as different pipe sizes or materials. Well-organized output makes it easier to find trends, catch errors, and create useful engineering reports. The best reports are concise but complete, giving clear insight without unnecessary detail. Python code, writing results. Save engineering results in readable report files so they are easy to review and share. Use clear labels and units to avoid confusion, such as when reporting a beam deflection summary. For a simple beam calculation, define the key inputs: a load of 1200 newtons, a span of 2.4 meters, and an elastic modulus of 200 billion pascals. These values provide the basis for calculating the beam's deflection and stress. The beam section is defined with a width of 0.05 meters and a height of 0.10 meters. These dimensions are used to calculate the moment of inertia, which helps determine beam deflection under load. The calculation results are saved in a report file for easy review and sharing. The rectangular second moment of area is found by multiplying the beam's width by the cube of its height, then dividing by 12. It measures how well the beam's cross-section helps resist ending by distributing stress. To find the center deflection of a simply supported beam, multiply the applied load by the span cubed as part of the deflection formula. This reflects how both the load and the beam length influence bending. This calculation finds the center deflection of a simply supported beam under a central load. The deflection is determined by dividing the load-related term by 48 times the elastic modulus and the moment of inertia. The code first converts deflection from meters to millimeters, making the result easier to read in engineering reports. It then begins the maximum bending stress calculation by combining the applied load, span, and beam height, setting up the stress value for the next step. To estimate the beam's maximum bending stress, divide the current stress value in megapascals by 4 times the moment of inertia, with a 1 million factor included to keep the units consistent. This gives the stress in megapascals. The program opens the report file for writing in a way that closes it automatically when finished. It adds a clear title, notes that units are included with each result, and records the applied beam load rounded to 1 decimal place in newtons. The code writes key beam properties to a report using consistent units and formatting. It records the span, width, and height in meters with appropriate decimal precision, and the moment of inertia in meters to the 4th power using scientific notation. This keeps the output clear, precise, and easy to read. The code records the key results in a clear report format. It writes the maximum deflection to 3 decimal places in millimeters, then writes the maximum bending stress to 2 decimal places in megapascals, making both values precise and easy to read. To check the saved report, open the report file in read mode using UTF-8 encoding, then read its full contents into a text variable. Using a with statement manages the file safely, so it closes automatically after reading, even if an error occurs. First, display a message showing where the report was saved, so users can locate the output. Then print the report's contents to confirm the data was written correctly and to review the results quickly without opening the file separately. This script analyzes a simply supported rectangular beam under a given load. It uses the beam's span, material properties, and cross-section to calculate the moment of inertia, maximum center deflection, and maximum bending stress. The results are saved in a clearly labeled text report, then read back and printed to confirm the report contents. Formatted results. Formatted results turn raw data into clear information that others can read, check, and use. In engineering reports, this means showing what was calculated, the conditions used, and why the values matter, with consistent decimals, alignment, and presentation. Clear formatting makes key results, such as deflection or stress, easy to find and helps reviewers verify whether a design meets its requirements. Engineering results should use a level of numerical precision that matches the accuracy of the data. Too many digits can clutter a report and imply false accuracy, while too much rounding can hide important differences. Keeping precision consistent makes values easier to compare and helps prevent misinterpretation. Consistent formatting makes engineering reports easier to review, compare, and integrate into larger documentation workflows. Predictable structure and clear labels help different audiences quickly find what matters, whether they need detailed calculations or a high-level summary. This makes reports more reliable records for decisions across areas such as energy analysis and manufacturing quality control. Python code formatted results. Present engineering results in a readable report by using clear labels, consistent alignment, and appropriate units. Summarize the results in a small text report file so the information is easy to understand and share. This beam design case is an aluminum cantilever bracket. The key inputs are a beam length of 0.85 meters, an applied load of 420 newtons, and an elastic modulus of 69 billion pascals. Together, these values define the setup needed to calculate the bracket's stress and deflection under load. The beam section is defined with a width of 0.04 meters and a height of 0.012 meters, using an allowable material stress of 95 million pascals. Its moment of inertia is found by multiplying the width by the height cubed and dividing by 12, which indicates the beam's resistance to bending under load. The beam analysis finds 4 key quantities: tip deflection, maximum moment, maximum stress, and factor of safety. Tip deflection is based on the load, beam length, elastic modulus, and moment of inertia. The maximum moment is the load times the beam length, and the maximum stress comes from that moment, the beam height, and the moment of inertia. Finally, the factor of safety compares the allowable stress to the maximum stress to show how much strength margin the beam has. The code prepares the beam analysis results for reporting by converting tip deflection from meters to millimeters, and both maximum and allowable stress from pascals to megapascals. These unit changes make the values easier to interpret in an engineering report. It then specifies the report file where the formatted results will be saved. The report is built as a formatted set of text lines for an engineering results summary. It begins with a title and case name, then presents the key inputs: beam length, applied load, and allowable stress. After that, it lists the computed results, including tip deflection, maximum stress, and factor of safety. Each value is formatted to a consistent number of decimal places, so the final report is clear, organized, and easy to read. The report file is opened for writing with UTF-8 encoding, so any existing content is replaced and text characters are handled correctly. The report lines are combined into one new line-separated string and written to the file. Using a managed file block ensures the file is closed automatically when writing is finished. The code confirms that the report was successfully saved, then announces a short preview of the formatted results. It displays only the key engineering outcomes, including tip deflection, maximum stress, and factor of safety. This gives the user a quick summary of the beam's performance, without showing the full report. The script analyzes an aluminum cantilever bracket by calculating tip deflection, maximum stress, and factor of safety from its dimensions and material properties. It converts the results into readable units like millimeters and megapascals, then creates a short text report. Finally, it prints the report location and previews the key engineering results. Units and labels. In engineering reports, units and labels are essential because they give results clear meaning. A number without units can be misread, which may lead to wrong design decisions. Clear labels show what was calculated, and units show how to interpret the value, making the report useful for the author, reviewers, and future users. When reporting computed results, always state units clearly and use them consistently. Mixing systems such as Celsius, inches, and meters can make conversions hard to verify and may cause serious errors. Descriptive labels, such as distinguishing inlet and outlet temperatures, help readers understand results without checking the code. This clarity is especially important in engineering, where ambiguity can lead to delays or unsafe decisions. Clear labels and units make text file reports easier to understand, archive, and compare. Each output line should state what was calculated, the value, and the unit, so engineers can interpret results correctly across different contexts. This precision helps prevent confusion between similar measurements, such as movement, elevation, flow rate, or emissions data, and makes the report ready for professional use. Python code, units, and labels. Engineering reports should use clear units and labels so every computed value is easy to understand. Well-written text files help preserve that meaning. The beam analysis is based on three main measurements: a beam length of 2.4 meters, an applied load of 850 newtons, and a maximum deflection of 3.18 millimeters. Together, these values define the beam's size, loading, and bending response for later performance calculations or reporting. The code computes a deflection ratio by dividing the maximum deflection in millimeters by the beam length expressed in millimeters. The beam length is converted from meters by multiplying it by 1,000. The final value is dimensionless and describes deflection relative to the beam's length. The report is built as a structured set of labeled lines for a beam calculation. It includes the title, beam length of 2.4 meters, applied load of 850 newtons, maximum deflection of 3.18 millimeters, and a deflection ratio formatted to 6 decimal places in millimeters per millimeter. including clear labels and units, makes the report easy to read and verify. The report is saved as a UTF-8 text file using a context manager, which closes the file automatically after writing. The report lines are combined with new line separators, so the output is neatly formatted. This efficiently creates a text report that includes the needed labels and units. To verify the report, the program reopens the saved text file in read mode using UTF-8 encoding, which helps handle special characters correctly. It reads the contents into a variable for checking, and the file is automatically closed afterward to avoid resource leaks. The code prints the saved engineering report, so you can confirm the file was written and read correctly. This quick check helps verify that the report's contents are accurate and complete. This script creates a simple beam engineering report with clear labels and units. It records beam length, applied load, and maximum deflection, then calculates the deflection ratio using consistent millimeter units. The formatted results are written to a text file, read back for verification, and printed as a neat report that is easy to check and understand. Custom Python modules. Importing custom modules. Importing a custom Python module lets you use functions from one file in another, helping keep engineering or scientific programs organized. You can separate detailed calculations into clearly named modules and import them when needed. This keeps the main script focused on the overall workflow while making the code easier to read and reuse. To import a custom Python module reliably, make sure its file has the right name and is stored where Python can find it. In small projects, keeping the module in the same folder as the script is simple and portable. As projects grow, grouping modules into topic-based folders makes the structure clearer and helps others find where key calculations and tasks are defined. A smart import strategy reduces errors and improves teamwork by keeping shared calculations in one module instead of copying them across scripts. This ensures updates happen in one place, and everyone uses the same version. Clear module names and consistent imports also make engineering projects easier to maintain and more professional. Python code. Importing custom modules. Custom modules help keep engineering calculations organized by placing reusable functions in separate files. This example shows how to import those functions and use them to produce a small labeled report. We import the path class from the pathlib module to work with file paths safely across different operating systems. It makes creating, reading, and writing files easier without needing to handle platform-specific path details. We define the path for a custom module file using the pathlib library, which handles file locations safely across operating systems. The module file, named beamtools.py, will store custom functions so they can be imported and reused later in the script. This code creates a string containing a small Python module. The module defines a rectangular area function that takes a rectangle's width and height, then multiplies them to find the area. The string can later be saved as a file, so the function can be reused elsewhere in the project. The bending stress function estimates the stress in a beam using its moment, width, and height. It first finds the section modulus by multiplying the width by the height squared and dividing by 6. Then it divides the moment by that value. The result is the bending stress in pounds per square inch, which helps assess the beam's structural integrity. This line saves the module code into a new Python file named beamtools.py in the current directory. Creating this module lets the main script import and use its functions, keeping the code more organized and modular. We import the Beam Tools module to use previously defined engineering functions, such as calculating a rectangle's area and a beam's bending stress. This lets the current script perform these calculations without rewriting code, keeping the work organized, modular, and reusable. The setup defines 3 beam inputs for later calculations: a width of 2 inches, a height of 4 inches, and an applied bending moment of 1,200 pound-inches. These values will be used to find the beam's area and bending stress. We use functions from a custom module to calculate 2 basic beam properties. First, the area function multiplies width by height to give the rectangle's area in square inches. Then, the bending stress function uses the moment, width, and height to find the section modulus and divide the moment by it, giving stress in pounds per square inch. A beam calculation report is built as a list of labeled text lines. It includes the report title, the beam width and height formatted in inches, the area in square inches, and the bending stress in PSI. These formatted lines can then be joined and saved to a text file to create a clear summary of the results. The report is saved by first creating a safe file path, then writing the report content to that location. The report lines are combined with line breaks, so the result is a readable text document. This creates a saved beam calculation report that can be opened and reviewed later. The program confirms that the custom Beam Tools module was imported, then displays the calculated area and bending stress with appropriate units and formatting. It also tells the user that a text report with these results has been saved and gives the file location. This script shows how custom Python modules can make engineering calculations clearer and reusable. It defines beam-related tools for finding rectangular area and bending stress, then imports them to analyze a beam with given dimensions and load. The computed results are formatted into a short report saved to a text file, while a console summary confirms the import and displays the area, stress, and report location. Reusable function modules. A reusable function module is a separate Python file that stores related calculations for use in multiple programs. This keeps common engineering computations, such as stress or flow rate calculations, in one stable place, instead of repeating them in every script. As a result, the main program stays clearer and can focus on the overall workflow. Reusable modules should be clear, reliable, and focused on one purpose. Group related functions together and avoid mixing unrelated tasks unless they directly belong together. Use clear function names with predictable inputs and outputs so the module is easy to understand and reuse. Good organization reduces errors and lets updates made in one place apply wherever the module is used. Reusable function modules help keep projects consistent, easier to maintain, and easier to test. By separating calculations from scripts that manage data or reports, you can verify the calculation logic before using it in larger workflows. In Python, a well-organized module can grow into a small project library where each part has a clear role and the code is simpler to understand, share, and expand. Python code, reusable function modules. Reusable modules help keep engineering formulas organized and easy to manage. In this example, one module is created and imported, while results remain clearly labeled with engineering units. We import the path class to work with file and directory paths in a platform-independent way. We also import lib utilities, so Python modules can be loaded dynamically from a file path at runtime. Together, these tools support managing paths and loading modules as needed. We create a Python module file for reusable beam calculation functions. Using the pathlib path class, makes the file location work reliably across different operating systems. The bending stress function calculates stress in a beam using the applied moment, the distance from the neutral axis, and the beam's moment of inertia. It first checks that the moment of inertia is positive, since the calculation is not valid otherwise. If the value is valid, it finds the stress by multiplying the moment by the distance and dividing by the moment of inertia. This function estimates the tip deflection of a cantilever beam from the applied load, beam length, modulus of elasticity, and moment of inertia. It first ensures the modulus and inertia are positive, because invalid values would make the calculation meaningless. It then returns the deflection using the standard beam theory relationship: load times length cubed, divided by 3 times the modulus times the inertia. The code creates a module file on disk by using a path object and its write text method. It saves the module code, stored as a string of Python functions, into the chosen file location. This makes the functions reusable later through import. We create an import specification so Python can load a module from a specific file location. Using the import library utility, Python is told where to find the beam calculations module through the stored module path. This enables the module to be loaded dynamically and its functions used without adding it to the standard Python path. We use the import library utility to create a module object from the prepared specifications. This makes sure the module is properly structured and ready to load its functions for use in the main script. The loader runs the module file so its functions become available to the script. This is essential because it lets the rest of the program call those functions when needed for calculations. This example defines a simple cantilever beam setup with a 500 Newton load applied over a 1.2 meter beam. The material stiffness is set using an elastic modulus of 200 billion pascals, and the beam's resistance to bending is represented by a moment of inertia of 8 times 10 to the negative 8 meters to the 4th power. The point of interest is 0.025 meters from the neutral axis, where bending stress is 0. The bending moment is found by multiplying the applied load by the beam length, giving a value in Newton meters that is used to determine the beam's bending stress. We use 2 beam calculation functions and store their results for later use. The bending stress function finds stress from the moment, distance from the neutral axis, and moment of inertia. The tip deflection function finds the beam's end deflection from the load, length, modulus of elasticity, and moment of inertia. The code converts stress from pascals to megapascals by dividing by 1 million, making the values easier to read. It also converts deflection from meters to millimeters by multiplying by 1,000, which is more practical for small engineering deflections. The report is built by choosing a text file name and collecting the report content as formatted lines. It includes a clear title, the beam load and length, the bending stress in megapascals, and the tip deflection in millimeters. Each value is labeled and rounded consistently, making the final cantilever beam report easy to read. The code writes the report to a plain text file using the previously defined file path. It combines the prepared report lines into one text block, with each line separated by a new line, then saves that content to the file, creating it or replacing any existing version. The program reports that the module file and report file were created successfully, confirming that the reusable functions and calculation results were saved. It then prints the key engineering outputs: bending stress in megapascals to 2 decimal places and tip deflection in millimeters to 3 decimal places. Together, these messages provide a concise summary of the beam analysis results. This example shows how to create and use a custom Python module for cantilever beam calculations. The module includes functions for bending stress and tip deflection, which are applied to a specific beam case. The results are converted to practical units, then summarized in a saved text report with the load, length, stress, and deflection. Running the script confirms that the module and report were created and displays the calculated values. Importing custom modules. Importing a custom Python module lets you reuse your own functions without rewriting them in every program. This is useful in engineering, where the same calculations often appear across projects. Keeping reusable functions in a separate file makes the main script cleaner, more organized, and easier to manage. To import a custom module reliably, place it where Python can find it, often in the same folder as the script that uses it. Use clear, descriptive file names that explain the module's purpose, and avoid vague names or names that conflict with Python libraries or other project files. A consistent folder structure and meaningful naming make projects easier to manage, share, and debug. Custom modules keep reusable calculations separate from the main project script. The module provides consistent, reliable logic, while the script handles inputs, assumptions, analysis, and results. This reduces duplicated work, prevents formulas from drifting across projects, and makes collaboration easier when module functions are clearly defined. Python code, importing custom modules. This example uses a custom engineering module to keep reusable beam calculation functions separate from the main script, so the script can focus on the overall workflow. The script begins by importing tools for file handling and dynamic module loading. The path class helps manage file paths consistently across operating systems, while the import library module lets the script load custom modules during runtime. We create a project folder to hold the custom module and output files, using the path handling tools from the pathlib library. The directory creation method is set to avoid errors if the folder already exists, so the script can be run repeatedly without directory-related problems. This section defines a custom module as text to store reusable engineering calculation functions. It includes a rectangular area function that takes width and height in meters, multiplies them to find the rectangle's area, and returns the result. Keeping these calculations in a separate module helps keep the main script cleaner and focused on the overall workflow. This function estimates the tip deflection of a cantilever beam using the applied load, beam length, modulus of elasticity, and moment of inertia. It applies the standard beam theory relationship, load times the length cubed, divided by 3 times the modulus of elasticity and the moment of inertia. The result shows how these physical properties determine how much the beam bends at its free end. The script creates a custom module file in the project folder and saves the module content into it. This makes the custom functions available for the main script to import and use. To make a project folder importable while a program runs, first use the system module to adjust Python's runtime environment. Then place the resolved project folder path at the start of the system path, so Python checks that folder first when importing modules. This lets the program load custom project modules smoothly. The import library lets us load the custom beam tools module only when needed. This gives the main script access to reusable functions for tasks like finding a rectangle's area and calculating cantilever beam deflection, while keeping the workflow cleaner and more organized. The script defines the beam's key input values, a width of 0.05 meters, a height of 0.1 meters, and an applied load of 250 newtons. These settings provide the basic measurements needed for later beam calculations. The code defines the main properties needed to analyze a beam: its length, the material stiffness through Young's modulus, and the cross-section's moment of inertia. The moment of inertia is calculated for a rectangular section using the beam's width and height. Together, these values support later calculations of how the beam bends under load. We use two reusable beam tools to keep the main script simple. The rectangular area function calculates the beam's cross-sectional area from its width and height, while the cantilever tip deflection function calculates the end deflection using the load, length, elasticity, and moment of inertia. Together, these functions handle the engineering calculations and keep the workflow clear. The report file is created in the project folder and saved as a beam engineering report. It records the calculated cross-sectional area in square meters and the beam tip deflection in millimeters. The values are formatted to suitable decimal precision, so the report is accurate and easy to read. The program confirms that the Beam Tools module was imported successfully, then prints the beam's calculated area and tip deflection with clear formatting. It also reports that a detailed engineering summary has been saved to a text file, so the results can be reviewed later. This script shows how to use a custom Python module to keep engineering calculations separate from the main workflow. The module contains functions for rectangle area and cantilever beam tip deflection, which the main script imports and applies to a beam example. It then saves the results in a report file and prints the area in square meters and the deflection in millimeters. Automated engineering workflow. Workflow report. A workflow report is the final record of a repeatable engineering process, showing how input data becomes results. In automated workflows, it documents the data used, the calculations performed, and the final evaluations in a form others can understand. A strong report clearly labels key details such as units, material or fluid type, and efficiency, so the meaning of the numbers is clear without reviewing the code. Effective workflow reports should be consistent, readable, and easy to compare across repeated runs. They should briefly describe the task, summarize the input data, present the engineering results, and note key assumptions or limitations. Clear labels and units give values the context they need, while good documentation reduces misread data and improves team communication. A repeatable reporting workflow supports traceability, verification, and accountability. It helps you identify where results came from, check whether outputs are reasonable, and keep a reliable record for future review. Even simple workflows build good habits through structured data entry, consistent calculations, and clear, reusable results. Python code workflow report. Use a repeatable engineering workflow. Read the inputs, compute the needed values, and report the results clearly. Keep labels and units visible throughout, so the work remains understandable and accurate. We import the path class from the pathlib module to work with file system paths more easily. It helps us read from and write to files in a clear, platform-independent way, without needing to handle operating system differences directly. The workflow begins by setting a location for an input data file, then creating a small comma-separated dataset with headers for case, flow, head, and power. This data is written to the file so it can be read and processed later. The pump efficiency function estimates how efficiently a pump converts input power into useful water power. It uses flow in gallons per minute, head in feet, and power in horsepower. First, it finds the water horsepower from the flow and head, then divides that by the input horsepower and converts the result to a percentage. This makes the function reusable for different pump conditions. The code reads the input file, trims extra white space, and splits the text into lines. It uses the first line as the headers by separating it at commas, then processes the remaining lines the same way. This turns the file into a structured set of rows, ready for further analysis. The data is first filtered to keep only rows with the same number of columns as the headers. This protects data integrity by ensuring each row has the expected structure. If any rows are excluded, an error is raised to flag the mismatch before further processing. The report is first set up with basic header details, including the title, input file name, and water as the fluid type. The program then processes each valid data row, reads the case information and pump measurements, calculates efficiency using the pump efficiency function, and adds the result to the report, rounded to 1 decimal place. The workflow report is saved by first choosing a report file location, then combining the report lines into one readable block of text with line breaks. That text is written to disk using the file writing method, so the workflow results are stored in a clear format for later reference. The code finishes by showing a brief completion summary in the console. It tells the user that the report was written successfully, how many input cases were processed, where the report file is located, and then displays the report text for quick review without opening the file. This script demonstrates a simple workflow for calculating pump efficiency from input data. It creates a small data file with flow rate, head, and power values, reads and checks each case, then computes the efficiency using a defined calculation. The results are saved in a report that summarizes the efficiency percentage for each case. When the script finishes, it confirms how many cases were processed and where the report was saved. Workflow report. A workflow report is the final output of an automated engineering process, turning calculations and data into clear communication. It should explain the context, name the data sources, and present results with clear labels, units, and assumptions. This helps readers understand and trust the findings, rather than treating the output as simple data storage. A well-designed workflow report improves consistency and quality control by automating routine engineering tasks, such as processing measurements and evaluating performance. Standardized structure and labels reduce errors, make reports easier to compare over time, and support clear communication with stakeholders. By fitting into the broader documentation process, the report becomes more than program output. It becomes a reliable tool for engineering decisions. A good workflow report should make the path from input data to conclusions clear for any future reader. Use plain language to name data sources, explain calculations, and present results in a logical order, with precise labels and units. This clarity helps others verify, update, and trust the work, turning automated computation into useful engineering insight. Python code. Workflow report. This example shows a repeatable workflow that reads input, computes results, and writes a report. Clear labels and units make the output easier to review in an engineering context. The code first imports tools for working with file paths and CSV data. The path handling tool helps manage files consistently across operating systems, while the CSV tool supports reading from and writing to comma-separated data files. Together, these imports prepare the program for the file management and data processing steps that follow. We begin by setting the workflow's input and output file locations using the pathlib path tool. One file holds the pump test data, and another stores the analysis report. This approach keeps file handling clear and compatible across operating systems. The pump test measurements are organized as a list of lists. The first list defines the columns: test ID, flow rate, pump head, and efficiency. Each following list stores one test's values in that same order, making the data easy to write to a CSV file later. The file is opened for writing with proper new line handling so it can be saved as a readable CSV. A CSV writer is then used to write all rows in a structured format, preparing the data for later reading and processing. The input file is opened as a CSV and read with a dictionary-based reader, so each row becomes a dictionary keyed by the column headers. This makes the measurements easy to access by column name. The rows are then collected into a list, so all the data is available in memory for later processing. The code first checks whether any measurements were loaded. If none were found, it raises an error saying the input file has no measurements. This stops the workflow early and prevents results based on missing data. The code prepares the data for engineering calculations by converting text entries into numbers. It extracts the flow rates, pump head values, and efficiency percentages from each data row and converts them to floating point values. This makes the measurements ready for accurate mathematical analysis in later steps. The pump test results are summarized with three key measures: average flow, maximum head, and average efficiency. Average flow and average efficiency are found by averaging their test values, while maximum head is the highest recorded head measurement, showing the greatest pressure achieved. The report is built as a set of text lines summarizing a pump test workflow. It includes the report title, the source data file, the number of tests, and key results such as average flow rate, maximum pump head, and average efficiency, each formatted with appropriate units. It also notes that the measurements are assumed to come from steady operating conditions, which provides context for interpreting the results. The code combines the report lines into one complete text block, with each line separated clearly. It then saves that text to the chosen report file on disk. Writing the whole report at once makes the process simple and efficient. The code prints a short workflow summary for the user. It confirms that the report was created successfully, identifies the input data file and the saved report file, and shows the average flow rate rounded to 1 decimal place. This gives quick feedback that the process finished and highlights the key result. This script creates a repeatable workflow for pump test analysis. It writes sample measurements for flow rate, pump head, and efficiency, reads them back, converts the values to numbers, and checks that data is available. It then calculates key summaries, including average flow rate, maximum pump head, and average efficiency, and saves them in a readable report. When run, it confirms that the report was created and shows the average flow rate, supporting clear engineering review with labeled units and assumptions. Workflow overview. An automated engineering workflow turns raw data into documented results with little manual effort. It typically reads data, performs calculations, and creates reports that record inputs, outputs, and assumptions. Its main value is consistency, so design cases, lab trials, and simulations are processed the same way and support reliable decisions. A repeatable workflow works best when each stage has a clear purpose. The input stage collects and checks data. The computation stage applies formulas and reusable functions without file handling distractions. And the reporting stage explains results with clear labels and context. Keeping these stages separate makes the workflow easier to update, adapt, reproduce, and communicate professionally. A workflow is a plan for reliable data analysis before coding begins. It should account for data from sources like instruments or spreadsheets and handle irregularities, making the full data path easy to trace and review. This matters in areas such as energy audits and quality control, where calculations affect cost and safety. Building workflows helps students turn raw data into organized, defensible engineering insights. Python code workflow overview. Show a simple automated engineering workflow by reading inputs, computing outputs, and reporting results. Keep all files small, organized, and clearly labeled. The code first imports tools needed for the workflow. It uses the path class to manage file system paths in a convenient, platform-independent way, and the CSV module to read and write CSV data. This workflow begins by setting two file locations, one for the beam calculation input data and one for the output report. The input file stores the cases to be analyzed, while the report file records the calculation results in an organized text format. The workflow input data is organized as rows, with a header naming the columns for case, load, span, and moment of inertia. Two test cases are included. Case A, with a 450-pound force load, an 8-foot span, and a moment of inertia of 52 inches to the fourth power. And Case B, with a 600-pound force load, a 10-foot span, and a moment of inertia of 80 inches to the fourth power. This structured data will support later calculations and report generation. The file is opened for writing, so it can be created or safely overwritten. A CSV writer then stores the data in a structured format, using its write rows method to save all rows at once in a consistent, repeatable way. This function estimates the mid-span deflection of a simply supported steel beam with a center load. It uses the load, span, and moment of inertia, sets steel's modulus of elasticity to 29 million pounds per square inch, and converts the span from feet to inches so the units match the deflection formula. The calculation estimates the deflection of a simply supported beam with a load at its center. It uses the load, span length, modulus of elasticity, and moment of inertia to compute the beam's downward displacement, returning the result in inches. The workflow begins by opening the CSV input file for reading, using settings that handle line endings consistently across operating systems. A dictionary-based CSV reader then treats each row as a record keyed by the column headers. Finally, all rows are collected into a list of cases, making the engineering data ready for later processing. The code first checks whether any beam cases are available. If none are found, it raises an error to stop the workflow. This prevents later calculations from running with missing or incomplete input data. The process begins by creating an empty results list to hold the deflection values for each beam case. It then goes through each case, retrieves the load, span, and inertia values, and converts them to floating point numbers so they are ready for accurate calculations. The code computes the beam's mid-span deflection for the current case, using its load, span, and inertia values. It then stores the deflection together with the case details in the results list, so the information can be reported later. The report begins with the title Beam Deflection Workflow Report, then states the key assumption, a simply supported beam with a center point load. It also records the elastic modulus as 29 million psi, a typical value for steel and an important input for deflection calculations. A blank line separates this header information from the results to keep the report clear and organized. Each result is unpacked into its key values, including the case name, load, span, moment of inertia, and deflection. These values are used to build a concise report line that lists the measurements with appropriate units and formats the deflection to 5 decimal places. Each line is added to the report so it can be included in the final output. To finalize the report, the code combines the report lines into one text block with line breaks between them. It then writes that text to the chosen report file, saving it as a text file for review or sharing. The program finishes by confirming that the automated workflow completed successfully. It then shows the input file, the report file, and the number of cases processed so the user can quickly verify what ran and where the results are saved. Finally, it prints the full report in the console, allowing the user to review the detailed results immediately. This script automates a basic beam deflection workflow. It creates input data for several beam cases, calculates mid-span deflection for a simply supported beam with a center point load, and processes each case from the data file. It then writes the results to a text report and prints a short summary showing the files used and the number of cases completed. Overall, it demonstrates efficient data handling, calculation, and reporting for an engineering task. In this lecture, you learned to write computed engineering results to text files with clear labels and units, organize reusable calculation functions in separate Python modules, and create a small, repeatable workflow that reads input data, computes results, and writes a report. In the next module, Module 5, we will go over none. Thank you for your attention. See you all in the next lecture.